Hello, everybody. Let me just first take a brief moment to assure you, those of you who were worried, that I am not in fact dead, even though I was not in school today. And since I am not dead, I will, of course, teach you math. So, we are going into a new topic that takes a lot of slides to explain and might seem a little bit complicated at first. However, let me assure you, it is not nearly as hard as it seems. So please just bear with me, and I promise you, most of you will be experts at this by the time we are done with this video. The topic we are learning about today is called solving systems of linear equations. You'll figure out what that is. There's a whole slide on it a little bit later on. But one thing you do need to know, there are multiple ways to solve systems of linear equations. The way we are talking about today is by graphing them, okay? As we often do, or as I like to try to do, we're going to start with a word problem today so you see where a problem might come from that requires this approach. Suppose you're walking to school. Your friend is 5 blocks ahead of you. You can walk 2 blocks per minute, and your friend can only walk 1 block per minute. How many minutes will it take for you to catch up with your friend? Okay, might seem very, very simple to start with. It might end up being a tiny bit more complicated than you think when you try to solve it, but going the way that we're going to do it today, it'll be very simple. First thing we're going to do, make a table to represent the problem, starting with the time in minutes. We've got 0 minutes, 1 minute, 2 minutes, etc., and your friend's distance from start and your distance from start. Well, your friend is 5 blocks ahead of you, so your friend starts at 5, you start at 0. After 1 minute, your friend's at 6, you're at 2. After 2 minutes, 7, 4. After 3 minutes, 8, 6. After 4 minutes, 9, 8. After 5 minutes, 10, 10. And notice what we have found. We are now both in the same position, okay, 10 and 10, after this many minutes. So if we graph that, all of the solutions we just found, all of the solutions we just found, 5, 0, 6, 2, 7, 4, 8, 6, 9, 8, and 10, 10. Now I want to caution you, the ordered pairs that we are graphing are these, 0, comma 5, and then 0, comma 0. And notice I'm going to graph my friend's distance in red here and my distance in blue. Notice on the graph there's a blue line and there's a red line. So, and then I will graph 1 comma 6 and 1 comma 2 because we both have the time. The time applies to both of us, but the distance is going to be different. Okay, so I go ahead and I graph 0, 0 right here and 0, 5 right here. And then we go to 1 minute. I graph 1, 2 and 1, 6. Go to 2 minutes, 2, 4 and 2, 7. Notice I'm coming closer together. 3, 6, 3, 8. And it turns out that your graph will end up meeting right here, our magical point of intersection. This is at 5, comma 10. And so we have to think about what this means. 5, comma 10 is our solution, but it actually means something in the real world. In the context of this problem, it means that after 5 minutes, we will meet each other. I'll meet my friend at block 10. Okay? So that is the way that we solve a problem like this. And this brings up a brand new topic, a system of linear equations. A system of linear equations is 2 or more linear equations, means when you graph them, they're straight lines, that we consider together, means we plot them on the same graph. Okay? Feel free to pause the video and write that down. I'm going to go on, however, so when you're done writing, come back and join me. The solution or solutions to a system of linear inequalities, I'm sorry, this is wrong. I made a slight mistake. This should be equations. We will be doing systems of linear inequalities, but we're not doing them yet. So this should say equations. The solutions to a system of linear equations is or are the ordered pairs that will satisfy both equations. In the previous slide, that was the ordered pair 5, comma 10, because it worked for both lines. It was a point on both lines. One way to find the solution to a system is to graph the equations on the same coordinate plane and find the point or points of intersection. like we did in the last one, where they intersected was the point we cared about. There are three types of solutions that are possible to get when solving a system, and we'll talk about each of these coming up right now. Okay, pause if you need to keep writing stuff down, otherwise I'm moving on. Type 1, we can have one solution. This is probably the most common type of solution, or sorry, the most common type of problem that we'll get with systems of linear equations. You notice it intersects at exactly one point, these two lines. So that means one solution. What that means, this happens when we have two lines that intersect in exactly one place. And to have this happen, the slopes of the two lines will have to be different, because if they were the same, you know the lines would be parallel. And so it would not intersect at exactly one point. The next type, or I'm sorry, here's a problem like we would have for that. The way we figure out just by looking at the equations whether or not it has 0, 1, or more solutions is by looking at the two equations. If I look at these two equations here in green, then, and I solve both to get it into slope-intercept form, I notice my slope here is 2, and my slope here is -3. So what did we find out about the slopes? They're different. So how many different solutions? Oops, sorry about that. They are different. And so how many solutions will there be? Just one. And this will always be the case when you have different slopes. You will have one solution. Here's the next type. There can be no solution. Look at the graph here and look at the point of intersection. Notice the lines are parallel, so there is no point ever where the two lines will meet. They will stay the same distance from each other forever. Okay? So this happens when the lines never intersect. There is no solution, and the lines will be parallel. So in order to have no solution to a system of linear equations, the slopes will be the same, but the y-intercepts will be different. Notice my two y-intercepts here. I've got one at 2 and the other one at -2. Okay, so that's how you know that you will have no solutions. It's when the slopes are the same, but the y-intercepts are different. And we're going to figure out how we do that. We start with two different equations here now, the ones in green again, and I get them both into a slope-intercept form. The first one's already in slope-intercept form, so my slope is -5. The second one, I have to massage into it, but eventually I get that the slope is also -5. And so I know that these are going to be parallel. And then I look at my y-intercepts. I notice my y-intercepts are different. So I know that these two lines are going to be, first of all, that the slope is going to be same. So same slope, different y-intercept, or different b. So how many solutions will there be? No solutions. Okay. Finally, the third type, there can be an infinite number of solutions. This happens when the lines overlap. Notice down here, what's drawn? We have a red line that is dotted and a blue line that is solid. The red line is dotted just so that you can see there are two different lines there, but they're actually right on top of each other. And so it's pretty obvious that this point right here that I'm drawing will be a solution to both lines. This point right here will be a solution to both. This point right here, this point right here, this point right here, etc. There will be an infinite number of points that's on both lines. Okay? So what we say is the lines will be the exact same line. The slopes, again, because it's the exact same line, the slopes will be the same. And the y-intercepts now will also be the same because it's the exact same line. And so you know when you have same slope and same y-intercept that you're going to have infinite solutions. Once again, we start with two equations. We'll have to solve them both to get them in y equals mx plus b form. And once we do, if we look and we see that the slopes are the same, so 2 and 2, and the y-intercepts are the same, 1 and 1, which basically means I have the same equations, then you know that you will have infinite solutions. And we'll just write that out. What do we find about the slopes? Same slope, so same m, same b. How many solutions? Infinite solutions. I abbreviate the word solution, SOL apostrophe N, and I'll just pluralize it, put an S at the end. Okay, so let's just sum up what we just learned. How can you quickly decide the number of solutions a system has? First of all, one solution happens when you have different slopes, and so those would be different lines. No solution will happen when you have the same slope, which means the same slope, but a different y-intercept, which means your lines are parallel. And finally, infinitely many solutions happens when you have the same slope, the same y-intercept, because you have the same line. Okay? So really, the key part here is if you have different lines, you'll have one solution, as long as they're not parallel. If they have parallel lines, you'll have no solutions. If you have two lines that are the same line, you'll have infinitely many. Now let's go on to figuring out how many solutions we have. This first one, how many solutions does the following system have? Well, we look at our slopes. Our slopes are different. We look at, well, we need to look at nothing else. If we have different slopes, we know that they will eventually intersect somewhere, and so we have one solution. Next one, how many solutions does the following system have? Well, this one's in y equals mx plus b form, but the top one is not, so I need to rearrange it. 3x minus y equals negative 2. I'm going to add 3x to both sides. And I have negative y equals 3x minus 2. And then I'm going to multiply everything by negative 1. Multiply by negative 1, multiply by negative 1, multiply by negative 1. And what that really means is I'm just going to flip the sign on everything. Y equals negative 3x plus 2. So now I have two equations. I have this equation here, this equation here. Notice it might look like they have similar slopes, but they are opposite slopes, which means they are different. You have different slopes. It doesn't matter if they look the same. You're going to have one solution because the lines will eventually intersect. Moving on. How many solutions does the following have? I'm going to leave this one for you to do using your notes that we've already taken. I want you to rearrange the necessary equations to get them in both to be in slope-intercept form, and then tell, based on that, how many solutions they have. And then we're going to move on. So once you have graphed two linear equations, as you see here, this is already graphed for us. We have y equals negative 3x minus 1. That's the red line. We have y equals 4x plus 6. That's the black line. Once we have graphed them and we seem to have an intersection, right here, it looks like we have an intersection, right? And it looks like it is right here on the point. Well, you tell me, what point does it look like it is? If you said negative 1, 2, you're absolutely right. However, just because it looks like it doesn't mean it's necessarily true. What if this was really the point negative 1.1 comma 2.1 or something like that? The point is we need to check to make sure that what appears to be right on our graph is actually right, because graphing is not 100% precise. Here's the way we check our work. We're going to look at the solution that it looked like we had, negative 1 comma 2. And we're going to start with the two equations that we were given. We started with y equals negative 3x minus 1 and y equals 4x plus 6. Well, I'm going to plug this point, negative 1, which is my x value, as everyone knows, and 2, which is my y value. I'm going to plug it in every time I see an x in the first equation, right here, and every time I see an x in my second equation. I'm going to plug in y every time I see a y in my first equation and every time I see a y in my second equation. And then I'm going to look to see if my equations give me true solutions or true statements. Well, let's see what happens. I plug in 2 for y. I plug in negative 1 for x. I simplify. This gives me 2 is equal to 3 minus 1, which simplifies to 2 equals 2 minus, so 2 equals 3 minus 1, which is 2 equals 2. I know that this is correct, so it checks out on the first one. Now let's check it on the second one. Y is 2, x is negative 1. So 2 equals negative 4 plus 6, which means 2 equals 2, which means I'm right again here. So this was, in fact, a solution. Once you have two check marks, you know that you had your solution correct. Okay? And then you can call yourself done. So we're going to do a full example now. We're going to solve this system of linear equations by graphing. So First thing I need to do, I want to put these both into y-intercept form. Notice I have, because this is a system of linear equations, I have two equations. I'm going to graph them both on the same line and figure out where they intersect, if they do at all. I want them both in slope-intercept form. So I start with 2x plus y equals 5. I subtract 2x from both sides. I get that y is equal to negative 2x plus 5, and I'm done with that one. On the next one, I start with negative x plus y equals 2. I add x to both sides, and I am left with y equals x plus 2. Now I have two things that I can graph, and I will graph them on the next page. Step 2 is I plot the y-intercept as we've been doing. The y-intercept of the first one was 0, 5, or that's the coordinate of the y-intercept. The y-intercept is just 5, but the coordinate is 0, 0, 5, and I plot that. That's right here. Then I take my slope, which is negative 2, and I use that by going down to right 1, just like we have done. And that gives me 2 points. So I go down to right 1, gives me a second point. I connect my points, and I have my line drawn. For the next one, I do the exact same thing. Y-intercept was 0, 2, or the y-intercept was 2, so the point is 0, 2. That's right here. The slope was 1, so that means I go up 1 over 1. And that gives me my second point. I connect those points, and I have that line. So up 1, right 1. Okay? And I look to see where they intersect. It appears that they intersect right here at the point 1, 3. However, I'm not done, even though you're tempted to be done right now. You have to do this next step. It looks like they intersect at 1, 3, but we need to check it. You absolutely need to check it every time. So we plug in 3 for y, we plug in 1 for x, and we see if we get a true statement. Does 3 equal negative 2 plus 5? Yes, it does. So I have a true statement. But we also have to do it to the other equation. Y equals x plus 2. Y is 3, x is 1. That means that 3 equals 3, and we have a correct statement there as well, meaning that this point right here that we drew that looked like 1, 3 is in fact 1, 3. So this right here is the solution of our system of equations. And that's all there is to it. Let's do another example together real quick. Solve the system of equations graphically. 2x plus y equals 3, x minus 2y equals 4. Once again, I want to rewrite into slope-intercept form. So I subtract 2x from both sides, and I get y equals negative 2x plus 3. On the next one, I need, once again, to solve for slope-intercept form. So I subtract x from both sides. I get that negative 2y equals negative x plus 4. I still don't have y by itself, so I divide by the coefficient, divide by negative 2, but I have to divide by negative 2 on both sides. And so I get y equals 1/2 x minus 2. Notice how they write this real quick. This we have written as negative x plus 4 divided by negative 2. That is exactly the same thing as if I were to say, let me just cover this up for a second. I just want to point out that that's exactly the same thing as doing this. Divide by negative 2, divide by negative 2. It means exactly the same thing, and you get exactly the same answer. So either one way you want to write that is fine. I move on. I'm going to graph each of these. I'm going to breeze through this because we totally know how to graph linear equations. The y-intercept was 3, so the point for the y-intercept was 0, 3. My slope is negative 2. So for the slope, that means I go down 2, right 1. So I start here, go down 2, right 1, right here, connect them. I have my first line. For the next one, the y-intercept was 0, negative 2. My slope was 1/2. So that means I go up 1, right 2 from my y-intercept. So I start at my y-intercept, up 1, right 2, have a point, connect the points, and I have my line. Now, step 3, figure out what the point of intersection looks like. It looks like it's the point 2, negative 2. Perfect. Now I have to check it, though, to make sure it actually is the point 2, negative 2. And we're going to do that on the next slide. So we start with 2 comma, sorry, 2 comma -1. I might have messed that up. I don't remember what I just said. But we start with the point 2 comma -1. -1 is going to be replaced for y. X is going to be replaced with 2. Does -1 equal -4 plus 3? It absolutely does. So -1 equals -1, and I know I'm right there. Next one, y equals 1/2 x minus 2. Y gets replaced by -1. X gets replaced by 2. Does -1 equal 1 minus 2? Yes, -1 equals -1. And that one's right. Now that I've checked both of them, I can say I am, in fact, done. So, your turn. You are going to solve this following system of equations by graphing. Y equals 3x plus 4. 4y equals 12x plus 12. You're going to graph both lines. And if you get one intersection, you're going to check the answer. If you actually end up with lines on top of each other, you're going to say infinite solutions. And if you wind up with parallel lines, you're going to say that there are no solutions. Okay? And that is all. Thanks so much, folks.